Alrighty, so we're going to finish this problem over here on the homework. And so there was an error over here. So just to recap what's happening with this problem. So at 40 centimeters, the spring is in equilibrium over here. And it says over here that we want to compress the spring 10 centimeters. We don't want to compress the spring to 10 centimeters. So what does this mean? In other words, so we had those two alternating pictures today. So if we notice here, it was at 40 centimeters at 0 from equilibrium here. So this was at 40 here, centimeters. And we compress it by 10, which means we moved it 10 centimeters, right? And so that means that the distance moved from equilibrium is 10, right? So in this case, so in our equation, we know f of x is equal to kx by Hooke's law, and we know we have 60 newtons here, okay? And k is just our spring constant, and x is the distance it moves in meters, so 10 centimeters is 0.1 meters. And we solve this for k, and we get k is 600, all right? So in actuality, the k that we got earlier, the k of 200, was incorrect. Why? Because I assumed that we wanted the spring to move to 10 centimeters, not compressed 10 centimeters. So it's a very subtlety there. It's actually quite subtle. But I wanted to clarify that. So anyway, so what this does change in the problem is our k. So therefore, we know that the work being done is going to be equal to the integral from how far we're moving it, right? Of 600 times x dx. What we have to figure out now is we have to figure out how far we have moved this spring over here. And we have to think about it. So what's happening? So we moved, the first question over here is asking us how much work does it take to compress that 10 centimeters? Well, it's moving from equilibrium. So it's going to be 0 to, so it's from equilibrium. So it's not from this 0 over here. The 0 that we're thinking about is the equilibrium. So that means I'm moving it 10. So it's going to be from 0 to 0.1. Okay? So what this means now is we're going to solve this problem over here. So what we get, so the work is equal to 600 over 2x squared, going from 0 to 0.1, okay? And we solve this one, so w equals 300 x squared, going from 0 to 0.1. So we're going to get, I'm going to factor out the 300 because it's a constant. It's going to be 300 times 0.1 squared minus 0 squared, which is, of course, 300 times 0.1 squared, which gives us here 300 times 0.01, right? And then what do we get from there? Well, we just simplify this one, and we should get 3 joules. Yeah. And let's just make sure that all of this makes sense over here. So again, why is this one 0.1? Because we're moving it 10 centimeters from equilibrium. So it's the distance from equilibrium. We solve for k, put the k in here, anti-differentiate with respect to x, and plug in our limits of integration. And over here, we get 0.1 squared. It's going to be 0.01. Multiplying that value over there by 300, and we should get 3 joules. Okay. Similarly, over here, the other problem is going to be w equals the integral. It's going to be the same one. This time we're going to go from 0 to 0.15, as suggested in class, of 600x dx. And the problem follows in suit in the same manner. Okay? So this is essentially, so that was my mistake over there. I wanted to clarify it, so make sure have everybody understand that. Okay?